on transmission line cover a lot of bases, but how to implement them or how to realize the circuit is a totally different story. Because there's so many different type of transmission lines, so every one of them becomes a challenge. So for example, I'm going to give you a few examples, and we're not going to go into very deep details. I just want to give you an idea what you can do, what people have done in the past. So let's start with this. The lecture slides is under passive devices. So in transmission line theory, we often do a load, right? So let's say if this is a transmission line, we want to terminate it with a 50 ohms. Okay, that's fine. But what about when we have a waveguide? A waveguide by itself is not 50 ohm to start with, right? So the concept of putting a 50 ohm at the end of the waveguide to load it doesn't make sense. There's no resistor you can connect to where from the top metal to the bottom metal. I mean, that doesn't make sense. So in this way, you have to think in terms of wave. So for a waveguide, if a signal is coming in here, you can think of, well, how am I going to terminate this? What does that mean by putting this termination here? It means it just stopped the reflection. It means I just want to make sure there's no reflections back to my transmission line. So the way people do it is put a piece of material. This type usually is a ferrite type absorptive material called absorber. And then you design the shape of it. A simple shape would be like this, depends on what kind of power, how wide the bandwidth you want it to match. So the idea is like acoustic absorber. When the signal comes into here, it absorbs it and bounce back and basically absorb in this material and does not reflect. So this replaces the termination, the 50 ohms so-called, in waveguide. Right.
Quick question, Professor.
Yes.
So does it actually cover, like physically cover one end of the waveguide? That's what causes the reflections?
Yeah, so you actually cut a piece of material. Like in this case, I make it simple, just a triangular wedge thing, like and then just put inside, epoxy inside at the end of the waveguide. So there's a physical. There are different shapes. People do different shapes for different reasons. Either they have to handle higher power, widen the bandwidth, and whatnot. So, but the simple shape can be something like this.
I have a question.
Yes.
How do you connect to that? Like if you want this, if you want to, at the end of the day, you want to get your signal back, get your signal through the waveguide. How do you connect on that end?
On the other end?
No, on this end.
Oh, you don't. When you terminate it, that means you don't, right?
Oh, okay.
Right. So like if you later on,
what's the point of that then? I mean, you ultimately you want to get your signal from the waveguide. Why would you want to just block it off?
Only if this is a two-port network, but for multi-port network, then you will see later on, you want some ports to be loaded, to be terminated.
Huh, okay.
Yeah, I'll show you a few examples later. Okay. But when we say terminator in waveguide, sometimes that's what it means. The other examples, we talk about open stub and short stub. So when we have short stub, for a printed circuit or coaxial cable, you can think of just joining the top active line to your ground, so to speak, right? But what about for a waveguide? What does that mean when we have short? Well, we just have a short backing, just close it off with metal. But what if I want this short to be tunable? Sometimes we do. Okay, I'll show you examples why we want it to be tunable later. Let's say I want to have a short stub, but with a variable length. How do I do that? Because I cannot easily move the metal. So he said, no problem. I can put like a metal's punch in here, and just just slide this in and out, right? That would pretty much do the job. Yes, but that's a problem because how well can you ground this to the wall? If it's grounded really good, that means you cannot move the end. If it's not grounded well, then it won't work. This is high frequency you're talking about. So how can we fix it? People do something like this. Okay, what if I have a block here that is not totally ground to the end, but very close. So this is not exactly a short, right? But have such a high block to it, that means the impedance is going to be very low. So the narrow line is high impedance, wide line is low impedance. So this is low impedance. So then I'm going to do a quarter wave with very high impedance. Okay. And then another quarter wave with low impedance. So what does that do? Remember, quarter wave is a transformer. So this one is low impedance. Quarter wave later becomes high impedance. High impedance reflect here quarter wave. So you are at least as a ratio of C1 over C2 squared closer to short than just by itself. So if C1 and C2 is, C1 is the impedance here, which is very low. Z2 is the impedance of this line, which is very high. So this is a very, very small number. So even though this is not short, now the impedance looking at is not exactly zero, but with a very small number multiplied by a small number. So that is much closer to a zero. Right. So, and if you want to make this like, well, this is like very long length, quarter wave, can I make this smaller? Yeah, you can fold this. So you can fold the last block into here. So from here to here is quarter wave, from here to here is roughly quarter wave. So you still have an open to short, short to open kind of transition. Think about this, right? This is like, maybe it doesn't sound like a big deal, but when you try to use this, you will come back to this. The other thing you see people do is on the waveguide flange. So here, let me draw it on. So if I have two pieces of waveguide, rectangular waveguide, let's say, right? It's opening, and the other piece like here. How do I put them together? Well, people make a flange here, put some holes on the metal flange on both sides, and bow it together like this, right? So these two are the flanges, and bow it together, right? So now that works very well, very high frequency, except when you get to a little bit higher power, that becomes problematic. Why is that? Because when you put this together, these two contact, never really that smooth, right? I mean, when you have two pieces of metal put together, they are not exactly the same dimension. You're off by like 1,000 of 10,000, 0.0001 inches. You know, so I mean, if I exaggerate it, one would be like down here, the other one would be up here, or sometimes the corner is not that sharp, so you have a V shape, right? So you have some kind of structures here. Every time you have a different structure, you create a lot of mold, different mold. So instead of TE10 mold, you have other moldings. And then high power, those molds tends to propagate much farther and would cause a lot of problems, arcing and all that stuff. So to avoid this kind of problem, especially high power connections, people actually make a groove. So let me draw it. If I have a circular waveguide, for example, so this is my flange. This is my waveguide. I'm looking down into the waveguide. So people would cut a groove on here. I mean, it's hard for me to draw, but a groove here, and resets this part a little bit like this. So this is the groove I'm talking about, and this is the part that it resets a little bit. Okay. So what does that do? What does that do? So this is short, right? This is about quarter wave. So looking at from here, looking into the short, what do I see? People, answer.
Open circuit.
Open circuit. Now this is also quarter wave. Looking at the open, what do I see here?
Short.
Short. So even though they are not connected, I have a perfect short. Right? And because there's opens and I don't really care about the small mismatch. It's not going to be as problematic.
But the groove and the recess, they both have to be cut precisely to make a quarter wave.
Oh yes, this has to be model. I mean, most likely people will model in HFSS, make sure that works for the frequency range that they want, right? Yeah. Okay. There's a couple other things that we talk about for power divider. So in the lecture and in the homework, we talk about a 3-port network. We say you cannot have 3-port symmetrical lossless network, right? Remember, you cannot have symmetrical, reciprocal, and lossless network and well matched. And so in the homework, we say you have to give up something, right? So before we go into give up something, let's talk about the different type of T-junction or the junction. So for microstrip, for printed circuit, you have an input here, and you just connect this to output, right? That's not a good matching. It's not a good matching network. So we'll talk about how to match it later. For waveguide, you have different ways to connect it. So I can connect the signal coming in here, and then have 2 signals coming out. So I have 3-port waveguide, right? This is called the H-plane T-junctions. Or I can have the input coming down vertically and go out to the other side. That's called the output E-plane T-junctions. The difference is, if you look at, if I draw the arrow that represent the E field direction, of course it's going up and down. But what I'm saying is, if the E field is going up and down here, when they come to the junction, they still go in the same direction, up and down. So the output tends to be in phase with the input, or at least the outputs are in phase with respect to each other. But looking at the E plane here, the signal coming down, when you come down to junction, you see how the E field change. So one side is positive, the other side will be negative. That means the output of this 2-port has to be 180 degree out of phase. That's just the nature of the junction, right? We'll use this property later. I just want to point this out to you right now. Okay, in a few slides, you will see why this matters. Okay, so this is a homework we talk about. If you want to have a 3-port network, you cannot be both symmetrical, reciprocal, and lossless, right? And well matched. That's just not going to happen. So that was the map that we do. So how well can I match it? How well can I match the 3-port network? If I just do like this, like a microstrip, I just connect 3 lines together. How well would that match? What does that mean when I say not match? So then you do the calculations. You say, okay, I want that to be lossless. So any one row square would be equal to 1. So I solve for alpha and beta. And then I say the second line here, the off diagonal should add up to be 0. So I get another equations, put it together, assuming they both are real, then I can solve for alpha and beta. So alpha turns out to be 1/3. So alpha squared is 1/9, beta squared is 1/4/9. So in terms of return loss, 1/9 is 9.5 dB. Insertion loss is 3.5 dB. Right? So this is just from the calculations. Remember, 3 dB is the power speed. So 3.5 dB, that means you're half dB over the actual insertion loss is half dB.
Professor?
Yeah.
So it says, so did you put 1/9 in? So alpha squared is 1/9, right?
Yes.
because in this equation you said this equation you put alpha 1.9. Alpha is 1.9.
I didn't say alpha is 1.9. I put alpha square here because I moved this to 10.
It doesn't say alpha. Oh, I see. Okay.
Yeah. Yeah. So it's 20. Yeah. 20 log. Now it's 10 log.
Okay.
Good question. So the insertion loss, the S21 is 3.5 dB. That means you only a half dB above what it's supposed to be, right? Because half power is already 3 dB. So this half dB is called the mismatch loss. That means the loss is not due to the loss of the material or the circuit itself. It's due to the mismatch. My input is not 50 ohms. So this half dB is reflected back into my input port. That's what it means, the mismatch loss. So the mismatch loss is basically your it's 1 minus gamma squared. It's not transmission loss. Okay. Think about this. We have used this before, but we use that for transmissions, right? Because we say gamma square plus the transmission square has to be equal to 1. Reflected power plus transmitted power is equal to 1. Okay. But now, because this is not two-port network, so you have to rethink the relations. Here, down here, I also give you the, let me zoom it. I also give you the AWR circuit. So let's look at this. Can I see this? Can you guys see the circuit? Okay, is that better?
Yeah.
So you should try to build this circuit in AWR. If you have trouble, let me know. So you just put a T line, right? So you can see this. This is what the name of the elements you can find. So this is a T line, right? So you look for the T line, the ideal transmission line and the phase. And I just have it as default 10 gigahertz. 360 degree is one wavelength. That means this is 50 ohm line. I'm really not doing anything. I'm just putting a 50 ohm, 1 lambda here, 50 ohm, 1 lambda, right? So so basically I'm just saying I have 3 transmission line I'm connecting like this, and I have port 1, port 2, port 3 labeled, and so in the graph I plot, this is my S11 and S21. So this is my S21 magnitude, and this is my S11 magnitude. Okay. So the S11 is sitting about 9.5 dB. This is 8, this is 10, this is 9.5 dB. S21 is sitting somewhere around 3.5. 3 is right here, right? So this is exactly consistent with our calculations, with the calculations. Any questions? Have you played with? Yeah.
I have one. Conceptually, why is it not matched?
Why is it not matched? Because
it seems like if I mean, I know if you're looking at it like in circuits in parallel, it's different, but I don't know if that applies here. But you know, it seems like you're going through one branch and that's matched, and then you're going through the other branch and that's matched too.
But when you put 2 together, it won't match, right?
Right. Like I guess this is just like parallel circuits. Okay.
Right. So that means here is 50 ohms looking in here that appears to be 100 ohms. Right.
Okay.
So they would not match. Okay.
I see. Is it 100 or is it 25 or?
Are they in parallel? Are they in series or what are they?
Well, they're in parallel.
Parallel, so it's 100.
It would be 25 in parallel.
Oh, sorry, 25.
Okay, okay. So we could make them, then we could hypothetically make them match then, right?
You can hypothetically make this 100 ohms, 100 ohms,
Yeah,
right?
correct.
Then it will be matched, but only matched to this port. Looking at this port now, this port is 100 ohms, looking at 50 ohms and 100 ohms. And they're in parallel,
I see. Okay, thanks.
Yeah. So how can we make it so all 3 ports would be matched? Well, you have to break the symmetry. So here we are assuming 3 ports are reciprocal, symmetrical, and lossless. So you have to break it so that it would be asymmetrical. So that means it works for one direction and not the other directions. Or you make it lossy. Okay, so for example, just like what you talked about here, right? So you say, okay, I could have 150 ohms here, make it 100 and 100. That's fine. That would end up to be 50. And then to get 100 ohms back to 50 ohms, I'm going to use a quarter wave transformer. So quarter wave, if square root of this side is 100, this side is 50. That would give you about 70 ohms, right? Quarter wave transformer. So now looking at 3 port 1, port 2, port 3, they all are 50 ohms port. So that's good. But this only works if this is my input. Use it as a splitter, divider. These 2 are my output. Or these 2 are input and this is my output. But I cannot use this as an input and the other 2 as output, for example, right? So it's not symmetrical. So I break the symmetry and I make it work one way. Does it work well? Limited people use it, but there are a lot of restriction on this. Okay, not ideal. Okay. So what else can you do if this is not good enough? This is the simulation of the power divider you just saw earlier. Okay. Of this power divider. I encourage you to do that. Just get a feel of what AWR looks like, and what does the graph means to you. So to construct that, again, I just put a 50 ohm line, whatever wavelength doesn't matter, right? The wavelength doesn't matter if this is 50 ohms. I put one wavelength, and this is 100 ohms. I put a one wavelength again, and then I put a quarter wave transformer here, 90 degrees quarter wave, 70.7 ohms.
All right, quick question.
Yes.
Why is the 70.7 ohms after the 100 ohms?
That's the quarter wave transformer. So remember, yeah, go ahead.
Oh no, I'm just saying in the diagram, it's like first it's 50 ohms. If you could go back one slide.
Because this is 100 ohms.
100 ohms. Oh yeah, that's right. 100 ohms comes in from the 50 main
Yeah.
branch. Okay.
If I want this to match this 100, 100, 100, 100, 100 in parallel to make the 50.
Mm-hmm. Okay. Yes. Okay.
Okay. So if you build this in AWR, you name them 3-port network. So, and this is what you see. Let me explain what the result is. So this is S21. I mean, you can look at the scale down here. What is green represent is S21, which is the same as S31. Right?
Professor?
Yes.
So what does the vertical axis on that graph represent?
dB.
Okay, dB. Okay.
They're all dB. Okay. So the left axis are S1, S21. So here you can see, if you see the like the green, it say dB, S21, right? Left side. You see the L here, the left side scale. So that means you read this at the left scale is -3 dB. which is what it's supposed to be. You want the power to be equal split, so it's 3 dB each, right? At that frequency. Are you with me?
Yes.
Okay. And then you look at the pink one, for example. The pink one is S22 left side. So what does that mean? That is the return loss looking at port 2, right? But it's also left side, so it's only 6 dB. 6 dB return loss is not good. It's basically very bad, right? So this type of power divider, if you do it this way, it only match the input end. It does not match the output end. Okay. All right, but it does give you a good power split right at 3 dB. And then look at the other one. If you look at the dark curve, is S32. Again, it's left side. So this curve here, left side is this. So again, it's 6 dB. But what is S32 means?
From 3 into 2?
From 3 to 2, that means if I have a power, or actually from 2 to 3, I have a power going in here, some of the power will go into my port 3. And this is highly undesirable because that means these two output have no isolations. If you think of this as two antenna or two amplifier, for example, if one of the antenna being blocked, the signal being reflect, the reflection will screw up the other antenna also, right? Or if you have amplifier, if one of the amplifier blow out and it's going to screw up the other amplifier also. So most of the time when you do power combining or power dividing, you want to have some kind of isolations between these two channels in most applications that I have seen. This one does not get it, right? But what it does give you is, if you look at the blue curve, the blue curve is S11, is on the right scale. So if you look at that single frequency, I mean, this is the ideal circuit, but it's just basically like very good match. Exactly 50 ohms match on this side, on the input side. Right. Any questions? So I want you to be able to look at the AWR model or look at this graph and be able to tell, okay, what is this circuit doing? What is it doing? What does that do? Is that performing well? I mean, that kind of information you should be able to get from the graph. So when you do the examples, don't just like plot the graph and, oh, I did the graph and that's it. Try to think about what they mean, okay?
I have a quick question.
Yes.
Just like in the real world, like what's a good threshold? Is it like minus 30 dB or what?
Return loss?
Yeah.
I say it's usually minus 15. Better than minus 15 is good. Typical is 15 to 20. Sometimes I see spec to like 25 dB, but anything beyond that is just noise. The reason is, let's say here, showing in this graph, this is the ideal circuit. You hardly get this. You have like almost minus 80 dB return loss, right? This is just so unrealistic. I mean, any mismatch, you move the cable, this can jump up to 60 easily. This 20 dB, you can lose it easily. Remember, the lower this is, that means the smaller the number. This is 10 to the minus 8. To go from 10 to the minus 8 to 10 to the minus 6 is not that big deal. If you go 10 dB or 20 dB on top, that's big deal. If you go from 0 to if you go from 1 to 0.01, that's a big deal, right? That's like drop 99%. But if you go from 10 to the minus 6 to 10 to the minus 8, your fluctuation is like less than a microwatt, right? This is like you have to move a few watts to do that. So this can change easily. That's why these are the noise, right? Typical return loss minus 15 to minus 20, I would say. So the next one, this is I think it's described in your textbook very well, and it's very popular. It's called Wilkinson power divider. So what it does is not only is split the power, it can also provide match like this in all three ports, right? Remember 0 along the diagonal elements means well matched. It can do that. So, and the trick is they put a resistor here. So they put a resistor between the two ports. Okay. So, and this is the one that most likely you guys have to do for the antenna combining. So you come in here, you do a quarter wave transformer. Now this is square root 2, so that means it's 1.4 times Z0 times 50, right? So that's about 70.7. This is right here. And then this is back to 50 ohms. And the resistance is 2 times 50 ohms, so it's 100 ohms. Okay. So by doing that, everything's well matched. So let's look at the S parameter. Here, again, if you see it, you know this is well matched. You know it's equal power splitting because these two are the same, right? You know they are in the same phase because they both are +1 and there's no J in here. I mean, the J is outside, right? This is the ideal power divider circuit you want. And this will provide that. So go ahead.
Does this eliminate the problem where part of the reflection or transmission on port 3 is seen at port 2?
Yes, the isolations, right? That does it. Now, part of the reason it does it is because now, let me draw on this again. Now, let's say if I have a reflections go to from port 2, right? So the signal is going to go and then go to port 3. But part of the signal also comes down here to go to port 3. So it provides two paths for the bad signal, the reflections, right? And these two ports end up to cancel each other. They end up to have exactly 180 degrees apart. So that provides the cancellation of the reflections. That means port 3 does not see the bad reflections from port 2.
Is that because the resistor doesn't change the phase, but the other path,
yes,
with the half wavelength does?
Right, right. At least ideally, right? And how do you build that? That's another story. That's totally different story. We'll talk about this later. So mathematically, this is just basically what it is. Now, when you put it together, we say, what is S deca S? You get a matrix like this. What does that mean? You get a 2 here, not 1. What does that mean?
Lossless. Not lossless.
No. Yeah, not lossless. Because the power does.
Is it because you have a resistor there? It's dissipating power?
Yes.
Hmm.
Mm-hmm. Okay. So it's a lossy network, right? Okay. So now you can also build from the circuit design, which you guys will be doing. You just build a simple power divider. This is 50 ohm. Looking into here is square root 2 times 50, so it's 70.7. And then you put a resistor in between, make 100 ohms. And so now when you put everything together, everything looks pretty good. So here, this is your, now we're looking at the green, which is the right scale. If you look at this, it's the right scale. It's about 3 dB, right? Between 3 to 3.0133, 3 dB. That's the power split between these two, between the input and the output. And the match is the blue, is still very good. It's still 80 dB. I mean, that's like more than good. The isolation now is the pink line. It's also the white scale. It's also along the same magnitude. So you provide perfect match, perfect isolations, and perfect power speed on this ideal circuit.
And this one doesn't really show any dissipation, though. I mean, that's pretty close to 3 dB.
Yeah, the through power doesn't dissipate. Look, the through power doesn't dissipate. If you track the signal coming from the input to one of the output, it doesn't go through a resistor, right? Let me see if I can point that. So if this is
okay, I
my
see
input,
it. Yeah.
right? It doesn't go through. It doesn't have loss. Yeah. So so this is one of the most common power divider people use, especially when you do it when you're building. Other than waveguide, people don't do this in waveguide. On printed circuit, this is like one of the most popular for printed circuit. Coaxial cables, yeah, some people still build this in coaxial. So now to construct this, people bend this line, and the reason is when you build this circuit in the past project, if you physically build it, sometimes people just buy one of those resistor with leads, that kind of resistor from PHYs, for example, or from IEEE. You get one of those cheap resistor, right? And you put it in here, and that won't work because again, this resistor is way too big for not taking any space, any wavelength. These two lines are transmission line as unknown characteristics impedance. So when you put that in here, you don't really know what you're putting here. You have a transmission line of no impedance or unknown impedance, and then you have a chunk of resistor that doesn't work for high frequency. So that doesn't work. So people bend this and put a very, very tiny resistor. The resistor, the size is about 40 mils length. That means like 0.04 inches. Typically, that's how small it is. A lot of times people don't even put a cheap resistor there. Some of the circuit board has an underlying resistive layer. So you can just etch off the metal and that becomes a resistor. Yeah, so that can be very, very tiny. I'll show you a circuit with that kind of resistor later. Now, to go through the math, let me go through this. This one show, this is a 1 to 2 power divider. And then you go through the 1 to 3 power divider with similar logic. And so combine them together, you have 1 to 6. Right? In your case, you typically have 1 to 2, 1 to 2, 1 to 2, you have 1 to 4 power splitter for your 4 antenna if you're doing 2 by 2 or 1 by 4. Right. To go through the math, which I'm not going to, you can read the book. A lot of the older microwave circuits, they printed circuit especially, they always go through this even odd mode operations. What it meant is if you go, so a lot of the circuits, you can split it up, okay, what if they are even, the potential are even, like mirror symmetrical on both sides. What if they are not? So let me give you an example what they mean by even and odd mode. So let's say I have this is a transmission line. This is also a transmission line. They're next to each other on the same substrate. Right? So I want to know how does these two transmission line couple to each other. So looking at this, looking at just the metal part, this is what I'm looking at. So the electric field, if they are even, that means that these two, the electric field, are both in phase. So how do they couple? How do they couple to each other? This is called the even mode. But it can also have an odd mode coupling. That means when the electric field are out of phase, this is down. Right? So the field pattern or the way they couple to each other are different they had 2 mode, and of course, any real coupling is a linear combination of these 2 modes. So mathematically, they split this out, and I'm not going to go through this. If you're interested, I list out the circuits here and also in the textbook. But nobody really do this anymore. I mean, now the software is so powerful. So if you're interested, like how does that derive? How do we know this resistance is 2 times Z naught? You know, derivation is here. So you go through it yourself. Okay.
Excuse me, I'm confused about that again. Weren't there 3 ports?
What? Say it again.
Were there 3 ports in the odd mode circuit?
The odd mode? Yeah. So basically, you cut this in half. You cut this circuit in half. You look at one and the other side and say, okay, what if these 2 are even? What if these 2 are out of phase? One is positive, the other one is negative.
But they both say port 2, so should that be port 3 on the bottom?
Yes.
Okay, just making sure. I wasn't sure.
I don't know if they're doing it for both. Let's see the next picture. Is that both port 3? Or they only look at port 2? Yeah. I think it's supposed to be port 3, but I could be wrong. Read the textbook if I copy it wrong. Okay. So I'm not going to go through that. So all the derivation involved with what we learned in the past, or I fill in all the steps for you, where the textbook give you the overall formulas. So this is the derivation. This is how we get the 2 hour. Hour is 100 ohms. Moving on now, that's not the only way to do the Wilkinson. Sometimes people remember a transmission line, you can write it as a shunt cap and a series inductor, right? So you can also write the transmission line as a pi network, depends on how you put you can write it as 2 inductors, 1 capacitor, or 2 capacitor, 1 inductors. If I choose this network for my transmission line, I just replace the 2 transmission line with a shunt cap, inductors, and a cap here, and same thing here, cap, inductors, cap on the other port, and keep this 100 ohms. I achieve the same result. So, but not, of course, I mean, you cannot really build this in num elements at 10 gigahertz. I'm just using it to match the result later. Because if you look at the elements here, the inductance turns out to be less than 1 nanohenry. That's really hard to do. Even if you just have a wire, there's no turn, that's already a few nanohenry. So to get to that is like really hard to control. 0.4 puff, again, that's puff is 10 to the minus 12 farad. So this is like so tiny. Any parasitic is going to throw you off. So at 10 gigahertz, there's no way you can build this in num elements. But people have done this at 1-2 gigahertz. I've done that, which I show you the circuit also. This is, I think, is maybe 1.5-2 gigahertz range. That's what it looks like. These coils are the inductors. The patch are the shunt capacitor, and this is the 100 ohms. This is the one that I'm talking about. You see this dark little thing? That's the resistive layer underneath the gold. So when you etch off the gold, you see the resistor only, right? So you can control this to like very fine accuracy. And you can also tune that too with laser. Okay. Any questions? I know there's a lot of information. I suggest you to go back and play with the AWR circuits on this type, right? Yeah, on this type of circuits. The next one is called coupler. Coupler is a 4-port network. So the typical function is I want to couple some energy out of the line. So for example, input 1, output is 2, that's my through port. I want most of the signal to go through here, for example. But very often I want to tap out some of the energy for detections. So a lot of times, a lot of systems, they will say, okay, if I receive a signal, I will turn on all my power amp, for example. And how do I know I have a signal coming in or my antenna is picking up a signal? Well, I tap this off a coupler, like a 30 dB coupler. 30 dB coupler, that means I'm only taking 1/1000 of the power, right? So very little power, 0.1% of the power. I'm going to use that and go to my detector. So if I detect a signal, I turn off the rest of my circuit, for example. People do that all the time, right? In your phone and everything, there's always a coupler. 30 dB is typical, 20 dB sometimes, depends on what you want to do with it. So this is called a through port, and when the signal come out here, it go to the couple port, port 3. And the last port is what we call the isolations. This is there to capture anything reflect from port 2. When it come through here, it want to dump onto port 4. Okay. So the 4 port is called input, through, couple, and isolations. So there are 2 types of circuits. One is symmetrical. The other one is anti-symmetrical. Symmetrical meaning if I go port 1, then the power will go to port 2 and 3. If I dump a signal in port 2, then the power will go to port 1 and 4, for example. It's just symmetrical on both sides, right?
So this is functionally equivalent to the Wilkinson power divider?
This is more powerful. This one so if you want to make it a power divider, you make a 3 dB couple. So that means 3 dB, that means this couple port also gets 3 dB of power. So that means they're equal power speed, right? But a lot of times people don't do a equal speed. They use it as like a detector. I can make a 30 dB coupler, right? So just to make sure, how do I know I'm sending power through my antenna? Well, I can put a coupler there. If I detect the power go through this line, then I know, yes, I have power going to an antenna, right? Or how do I know I'm receiving a power? Same thing. Right. Okay. So if you put 2 couplers here, you can detect whether you have power coming in or power going out. Depends on how you oriented your coupler. So that's why they call it directional coupler, because it has the input port 1 here only go to couple port 3. It doesn't go to port 4, right? S14 is 0. You see that? Right. So it's very directional. Okay. So and then the anti-symmetrical is, if you look at this matrix, it's not a symmetrical matrix, right? Because it's symmetrical matrix. But what I mean is, if I looking at port 1 and port 4, so if the signal coming in port 1, it will split into 2 and 3, right? I'm looking at this column. If I look at this column, the power coming in 4, it will split into 2 and 3, but the phase, this is 180 degree phase. If it comes in port 1, they're the same phase. So that's what we mean by anti-symmetrical, right? Whether the output port are in phase or they are 180 degree out of phase. Depends on how you fit into the network. So the coupling, this is how we define the coupling, is really how much power going to 3 coming from 1, log scale. The directivity is 4/3. That means, okay, I'm not supposed to get any so how much power I get from 4 to 3 is supposed to be very small. I'm not supposed to get a lot of power here, right? It's supposed to be isolated. So if the directivity is good, that means most of the power will go to 3 and none will go to 4. Isolation is between 4 and 1. How much isolations, how much power I'm getting from here. So isolation is really D per C. Ideally, the isolation is infinity, the directivity is infinity.
Could the directivity be also port, the log of port 4 over port 2?
No. Not necessary. Depends on. Is that the same? No, not necessary, because unless it's equal split, 3 dB split, right? But right now we're not talking about 3 dB coupler.
So for directivity, you only care about the coupled output, not the through output.
Right. Let's say if I get a minus 30 dB here and I get minus 35 dB here, that doesn't mean I have a lot of directivity, right? That means like I'm getting signal in both ports. Directivity is like how much energy I'm getting here with respect to how much energy am I supposed to get in port 3. This is supposed to be much lower than that.
Okay.
So so sometimes we do a 3 dB split, the coupling. So it's called the 3 dB coupler. So again, you can have a symmetrical or anti-symmetrical. The symmetrical one would be the port 2 and 3, they're 90 degrees out of phase. The anti-symmetrical here, they both are in phase, but then if you go in port 4, they are 180 degrees out of phase. Right, so it depends on how you build it, you can get one or the other. Now let me come back to this. The 90 degree we call it 90 degree hybrids. That means 90 degree 3 dB coupler. It's very useful for those who are trying to do circular polarized antenna. You don't have to do extra line length. You can just do this and this will provide you the 90 degree phase shift already. Right? So instead of doing a Wilkinson power divider and then do a 90 degree phase shift on the transmission line, you just build the coupler. So how do you build a coupler? How do you make this matrix, make the circuits to match this matrix? One type is called the branch line coupler. So these are all transmission line. If this is 50 ohm, 50 ohm, 50 ohm, this is Z0 divided by √2, so that is like 35 ohm, something around that. And this is 50 ohm. Just that you already provide the function of this matrix. Let's look at just the phase considerations, okay? Because the amplitude takes more to calculate, but the phase. So let's say if the signal is going from 1 to 2, so it has a 90 degree phase shift with respect to the input, right? Right? Right?
Okay.
So if I look at the signal go to port 3, it has to go through 2 quarter waves. So this is 180 degree with respect to the input. So the phase shift between these 2 ports, 90 degree. Right? Get it?
Yes.
Okay. So a branch line coupler is a simple way to make a 90 degree phase shift with an equal power splitting. You do both in one shot. Okay.
Is the bottom line also lambda over 4 or quarter point?
Yes, it's a square. So let's say I don't think I have a physical model to show you, but you can build this in AWR very easily. Just build this in AWR and play with it. The other type of directional coupler is just a couple lines. So this is the input. This is a 50 ohm line. You go into here. This one you can remain 50 ohms, or you can change the impedance, change the width, and then go back to 50 ohms. So this is my through, and this is my couple port In this case, the couple port is on this side isolation. Is that right? I have to test that. Okay. So, and how close are these two lines put together? That's capacitive couple. Dictate how much coupling do you want. If you want 30 dB coupling, then you want this one to be far away. If you want 3 dB coupling, then you want these two to be very close together. Right. So this is one of the physical picture here. This is input, output, the through port, and then this is I think that's a 50 ohms here, so 50 ohms to ground.
So is that the isolated branch?
Yes, that's an isolated. That's port 4.
Okay.
So can someone build this in AWR and tell me, did I get this 2-port reverse? I think this is the couple port. This is the isolation port. I don't know why I draw it this way. Can someone verify that and let me know? Yes.
Build it where?
AWR. Just put it in the microwave office. Okay. See if you can put one model in. That's an
How do you
exercise.
do the coupling in AWR?
AWR, the transmission line, there's a couple line. If you go to AWR, let's see, AWR. So if you go to AWR, go to elements, transmission line. Let's just say T line for now. Ideal phase, right? You see this? This is the couple line. You have 2-line, 4-port network. This is it. You just have to do this, put the ports there, and you can tell me, right? The couple lines are here.
Oh,
Is that under transmission lines?
On the transmission line.
Hey, how do you control the spacing?
In this case, you don't. So in this case, well, first of all, to answer my question, you don't need to. You just, these are done with even and odd mode. But in reality, you say, well, I'm going to build this with microstrip. Now, for those who are building microstrip, listen to this careful. There are 2 things you need to do. You need to define your substrate. So do an M sub. M sub is a microstrip substrate. The dielectric constant, you need to know what dielectric constant you're working with. Duroy is 2.2, alumina is 9.8. You can Google this easily. That's just a dielectric material. H is the height of the substrate. You know, typically come with 10 mils, 15 mils, 20, 25, 50. So 62 mils, right? That's just how thick your substrate is. T is how thick is your metal plating. So they are, when you buy circuit board, they will tell you ½ ounce copper, 1 ounce copper, how much copper they put on top of it. And you can translate, I think ½ ounce copper is 0.7 mil, 1 ounce copper is 1.4 mils. That's just how thick this conducting layer is. Rho, you can stop it. That's just a resistivity. Loss tangent is the we talk about it at the beginning of the class. Loss tangent is the dielectric loss of the medium. Usually, if you look up the substrate material, they will tell you what's the loss tangent is. Typical 0.001 for alumina. And this is the effective dielectric constant. You just put the same as dielectric constant. So you need to have this first before you pull out any other microstrip line. So, and then once you define what substrate you're using, then you go to the microstrip. You see the microstrip tab here? You can pull out all the lines. Say, I want the line, I want a trace. I'm just going to pull out the simple M line. Right, so now this one, this width is 50 ohms. I know 50 mils. And the length, those you can change, right? How width, what's the width? And if you want to do a junction, okay, oh, I'm going from a thin line to a thick line, so I do a M junction, or if I do a T junction, I mean, there's all kind of stuff here. Here, and then there are a couple lines. If I have couple lines, there are more than 2. You can do a lot of things here. Let's see. Let me pick out the 2. MC2. MC filter is fine. MC lines too, right? Like this. And here it tells you the width, the spacing between the 2 lines that you can control, right? That you can change, and the length. So one more thing. Yeah, go ahead.
When it comes to the coupling of the transmission lines, does the spacing, is that like, is the desired spacing a function of the wavelength you're working with or the frequency?
The spacing is how much coupling you want.
Right, but that's like, let's say you wanted a certain coupling factor, so to speak. Would you have to change the spacing if you were working with a higher or lower frequency?
No, you change the length more.
Okay.
Yeah. Okay. So the other question is, okay, I can change the width. I get this give me the physical design, right? But when I do the circuit model, it tells me 100 ohms, 70.7 ohms. How do I translate into it? Oh, there's a lot of calculations online, but here you have a tool. If you go to the top menu of AWR, there's a toolbox. The first one is transmission line, TX line. So when you call this, can you see the table? Yes. Do you see the transmission line table?
Where number is it?
The microstrip. Do you see the microstrip I'm doing? No?
No, we're still looking
Okay.
at AWR.
Okay, so that means that's a different app. Okay. Now you see this? When you click on two transmission line, you get this table, this form. On top, you can choose microstrip, strip line, coplanar, waveguide, rounded, coaxial, slot line, couple line. I mean, you have a lot of choices. The first one is microstrip, and how do you use it? The first one, if you know what material, like Duroy is a popular, Duroy 5880, they already populate, already tell you the dielectric constant is 2.16. It's around 2.2. If you don't have the material, it's not on this table, you just type in your dielectric constant, right? Loss tangents is 10 to the minus 3. This is all conductivity, is the copper silver. You can change it and say, yeah, this is copper. So the copper conductivity. So this is the material property, right? Down here, you say, I want to make 100 ohms at 2 gigahertz. I want a 90-degree quarter wave. Give me the physical. So the physical layout is, okay, I want mils, yeah. So this is 1.121 inches. But if I want to do inches, that's how long the quarter wave at 2 gigahertz is. With this dielectric material, the width is 21.7 mils. Right. The height is, I'm assuming I'm using a 25 mil substrate and half ounce copper. If that's not true, you say, oh, I'm going to use a smaller 15 mils. You can change it and then recalculate this side, bottom arrow, right? Or if you say, well, I have 50 mils Y transmission line microstrip and I have 150 mils length, I want to know what impedance I have, then you click the top arrows. Well, you are at 47.5, it's close to 50 ohms. The electrical length is 12.4 degree at 2 gigahertz. Right? This is a very easy, very good tool to know.
Is this another program, or did you open that inside?
In AWR. So I